Hi, everyone. Good morning. I want to welcome everybody here. Is my screen still shared or it's not?
Yes,
Still shared?
Yeah.
Okay, hold on. Why is it not letting me unshare? Is it still shared for you guys? The
Yes,
screen?
the background, the desktop now.
Okay. Okay, let me see if it can let me unshare. Got it. All right, better?
Yeah.
Okay, so once again, good morning, everybody. Welcome the guests also who are joining. I'm very excited about the student presentations of their final project for the machine vision class. And we have 10 groups total who will be presenting over 2 days. Today we'll have 5 groups who are going to present their projects, and really looking forward to all of them. So just basic instructions for everyone. Everyone gets about a 20-minute time slot in which 15 minutes are reserved for your demo video and presentation. Please start with the title slide. Tell us the title of your project, and each group member introduce themselves, followed by the demo video, followed by your presentation. And we'll reserve 5 minutes for question and answers from everyone, including our guests, your classmates, and myself. Okay, and try and during presentations, I would like everyone to share the presentation. All group members should present some portion of your presentation. With that, we have 2 groups.
Professor?
Your sound, Professor, from your side. We can't hear you. We can't hear you, Professor. Oh.
Can hear him.
I think the connection broke. So, um, you, did you hear my instructions, or did I cut off before that?
We heard you, yeah.
We heard the
Okay, go ahead.
instructions.
Group one, start your share your screen and start presentation.
Okay,
Sorry about this.
that's okay. Hi everyone. Today we will present our project in the machine vision course under the supervision of Professor Mirza. It will be talking about how to convert 2D images into 3D models. I am Mohammad Alzyout.
And I am Ya'rub Haddad. Okay, go.
And this is the demo of our project.
So everyone, good morning again. As you see in this video, our project is based on the photogrammetry. The photogrammetry is considered nowadays as the most crucial concept in the extended reality, where it is spanning between the virtual, augmented, and the mixed reality. And at the end, it will create more realistic models and can enhance the gap between physical and virtual worlds. The XR now, the extended reality, is nowadays, let's say, widely used in the educational and training matter, where it can offers a very realistic models. Let's assume that the class of anatomy for the medicine student. It can offer them a model for a human body, let's say, with very high details like the body textures and organs. So the extended reality also, it can offer, let's say, free risk training, as there is no physical, let's say, no physical airplane in the aviation. As you know, in the aviation, the simulator in the aviation is already used maybe 20 or 30 years ago. And so this why that for a trainer, we will not offer them like 200 million airplane, in where somehow we can offer them a simulator maybe with 1 or 2 million, and it can serve many trainers. Next, Mohammed, please. So the photogrammetry, it is a new technique that uses the overlapping and high quality images in order to reconstruct a 3D model. This concept, the photogrammetry, involves with four things to be discussed later on in details, which are the image alignment, dense point cloud generation, and the mesh creation, and the texturing. The photogrammetry nowadays, it can overcome the challenges or the difficulties can be faced for the traditional 3D modeling, where it is a time consuming and require advanced skills for the, let's say, for the personnel who are in charge of taking the images. This technique now it can, let's say, save the time, and the skills for this concept is a little bit less. So it can be done, let's say, with more, a little less skills per personnel. Next, Mohammed.
Okay. Now I will go with the workflow of the 3D reconstruction, which includes the photogrammetry or videogrammetry. The difference between these techniques is the input, which is images or videos. We choose this environment to be replicated in our project, which is in between the Dodge Hall and Hannah Hall in the Auckland University. We just need to capture or scan the environment with some digital camera, and also the smartphone works. As we saw the cat statue at the end of the demo, it's just 5 minutes video captured by smartphone. Then those data will be imported to the reality capture. The first step is the alignment, which includes key points detection and matching, then the camera pose estimation, then the output will be sparse point cloud, then going to the next step, which is mesh model. In this step, the sparse point cloud will be converted into dense point cloud by adding more points, and the triangulation phase, which is generate some triangles between these vertices to get initial 3D structure. Then we have the texturing, which is adding the texture and color to this model, starting with UV mapping, texture generation, and apply texture on the on the model itself. Then it's ready now. It has to be exported in any format like FBX, which is compatible with Unreal Engine, OBJ, which is compatible with Blender, PLY, etc. Why high quality image capture is essential? Actually, the alignment phase, the first step in the 3D reconstruction, includes key point detection and matching. As we know, the key points or these features are the edges, the corners, some specified features in the images. So we need these images to be high quality. So these key points can be detected and extracted and matched between across multiple images easily. Then based on these images, camera position and orientation will be estimated by the reality capture software using the technology structure, the technique of structure from motion. And then the sparse point cloud will be generated based on those key points. We can see here some example regarding those key points. Those key points was detected by the reality capture. We took 4 images. In figure 1, we have sharp focus and the clear image. In figure 2, 3, and 4, we have some problems. In 2, we have out of focus image. In 3, we have noisy image by increasing the ISO to 10,000. All the first 3 images were taken by the tripod with to get the, to be blur free. Then we took one more image by hand, which is the blur image, figure 4. We can see in those figures that the key point detected in the first figure was around 99,000 features, which is the best, which is accurate. But in the out of focus and the blurry images, we have very lowest number of key points. And in the noisy image, we have a lot much key points, but they are incorrect because of the noise. So our target to have sharp focus and clear images. So we have correct, accurate key points.
So returning back for the base of the images and the images for formation, as we learned in our class, it is the base of our project. So can you go for the next slide, Mohammed, please? Now we are talking about the exposure triangle, and we can start, let's say, from the shutter speed. We are talking about this that because one of the most crucial issues in this project is to get a high quality images, and the high quality images can come from the accurate and the perfect adjustment for the camera, as the shutter speed, as you know, it is controls the exposure time. Whenever we are having less time, okay, that we are having, let's say, more sharp image, while if less shutter speed, that will lead us for, let's say, more maybe blurry images. So at the end, the value of the shutter speed that used to capture a static the scene using that tripod or a robot in order, maybe that can enhance the image quality. Next, Mohammed, please. The other matter, which is also important, is the aperture. As the aperture, it is the, you know, the lens or opening. If we are having a wider opening, that means we are having more light, and the narrow opening, let's say, less light, and we have to get the best image in this for the aperture. We have to adjust, let's say, the value of the aperture. We need to make it something in the middle. We don't know, let's say, high quantity of the light, and also we need something in between, something like between, as we learned maybe in the extra credit project, something in between. So in our project, that it was between F8 and F11, it was enough to get the depth of the field as needed. Next, Mohammed, can you go? And the ISO also it is important as it is control the sensor sensitivity of the light, because the ISO it makes the amplification of the light coming through the lens of the camera. So what we need in this way, we need to minimize it as we can in order not to, let's say, extend the noise coming through the image. Next, Mohammed. So at the end, the main target of the exposure triangle is to make the balance between these three things: ISO, shutter speed, and aperture. Something, let's say, we need to balance them in order to get the best image, which is can we extract the features from it in the through the software used for this project. Oh, Mohammed. One of the things that it can be used to enhance the image quality is using a timer or a remote control. The timer of the camera and the internally one, and the remote control. Some cameras sorry.
Yeah, go ahead.
Okay. That timer and the remote control, they can enhance the image quality. How? Even maybe sometimes when we press the camera button, it can produce a very small shake. This shake, we need to avoid it, okay? And avoid any blurry features coming through the object taken photo for. So we can use the timer or the remote control in order to get this image the best quality. Next, Mohammed. And the optimal scene, let's say, for as we are enhancing, let's say, adjusting the camera we need as our scene. So our scene is the best scene can be taken to be well lit, flat textured surface where we can extract the features from it, wide and open space where we can move the camera in front or behind, left, right. We are having a fine space for that, and with minimal reflecting and transparent. Why? Because maybe this reflective surfaces can show the reflectance in the many places. In order we are changing the camera location. For the next slide, can you go, Mohammed?
Okay. But let me add something on this slide. In the optimal scene, we can capture by orienting the camera perpendicular to the surface and moving laterally to take capture images while preserving 60% overlapping, as we see in the lower right image. In reality, we have suboptimal conditions such as plane surfaces without textures, such as reflective, transparent, narrow spaces, complex spaces, and low light. For the plane surfaces, we can take images from more distance to have or include some textures from around surroundings. For the reflective surfaces, we can using polarization filter. For the transparent surfaces, it will be ignored totally. If we have enough images to that area, the transparent material will be ignored in the 3D reconstruction. In the narrow spaces, we need to take from some angles the images to have enough features in the images. In the complex, we need more images. In the low light, we need to maybe increase the ISO or use some external light source. This is an example of using polarization filter. We can see in the lower left image, this is the normal without filter. The one in the middle using the filter, but before adjustment, the angle. Then we can see at the right how adjusting this polarization filter will ignore this reflective area. And this is the pattern how we take these images. We have some rounds from many elevations around the object to be captured. Here we can see how the overlapping between images, as we can see the same point or feature in several images. It should be seen so we can align these images together. So this is why we need at least 60% overlapping between successive images. And here we can start talking about the reality capture software, which is the software we are using to generate the 3D reconstruction, to the 3D model, I mean. Actually, this software now is part of Epic Games, and also it is integrated to Unreal Engine. I don't want to spend more time about the details, actually, because we have no more time. The first step is importing images or videos to this by either input or using folder, or just drag and drop the folder containing these images. For the alignment, we can choose this choice, align images, to start the process of the alignment between these images to end up with the sparse point cloud. Then we create the mesh model as we saw in the demo video. And these are some details about this step, the mesh model generation. And here is the texturing. We have two choices, colorize or texture. The difference between them is colorize is just adding the color to the vertices, to the points of the point cloud, and interpolate the area or the triangles between them, while the texture is taking some images from the images, captured images, and put on top of these triangles between these vertices, which is better. Actually, we can get some, let's say, high quality from the texturing, better than coloring. And sometimes we end up with high poly models. As we saw in the demo, we have around 2 million triangles, which is very hard for rendering in VR simulations. So we need to simplify this model somehow using the simplification step. Then after the simplification, sometimes it happens to the texture to be distorted because there's some merging between these adjacent triangles. So we need to reproject the texture from the original, the high poly model, into the low poly model. And then it's ready to be exported and used in any platform. We have so many file formats. And this is the conclusions and summary. Actually, we saw how high quality images are very important. The settings need to be chosen carefully. The photogrammetry itself, it is transforming images into 3D models. Overlapping images are crucial, and the simplification, how we can use it to optimize the model itself. And we can see how photogrammetry accelerates the adoption of XR in education and training. Thank you. We are ready now for questions, if there.
Thank you, Mohammad and Yara. Good job.
Thank you. Thank you, Professor.
Okay, if you can unshare your screen.
Yep, sure.
Thank you. All right, before we start, we know we have a few guests who joined. If they want to introduce themselves, so our students also know who's here, please go ahead, unmute your mic and go ahead. I see Larry there.
Yes, good morning, everybody. I was a couple minutes late. I'm sorry. I'm still dressed pretty well here. I'm coming from the floor, so I was able to find a small conference room here. So my name is Larry Silagi. I'm from Stellantis. I'm working for Stellantis for 10 years. I'm controls and robotics manager, and I'm working in automotive industry for 25 years. I did have the chance to listen to your presentation from the beginning, and I think the image processing, digital twin for an image that's surrounding us, it is going to transform our lives a lot from a technology standpoint. Is not only that automotive industry trying to introduce that type of image capturing quality for autonomous driving, is the same thing used for coordinated motions for robots. So the data quality of the images, the data capturing of the images, and data processing of those images, it's for sure is going to be the next wave of the technology. That will going to enable a lot of new opportunities for motion, for controlling the environment around us. So very well done, very specific information, very well presented. Thank you, and I want to
Thank
thank you for the way you capture all the steps and everything. I do have a question for you.
Yeah.
What is the size of the file that the digital twin file after you capture the image and you create the 3D model in terms of size? How big was that file?
I didn't check that, but give me just.
So we have very similar situations for in automotive plants where we're building, we're doing the body assembly systems. When we combining new technology with the old technology, it's very important for us to have a good understanding of the existing systems. So we also using similar image capturing solutions. And after we obtain that image and we create the digital twin for that, we pretty much have around 400 or 500 gigs of data. Is that
Yes,
big?
yes,
So it's a huge data storage cloud.
Yes.
But can be sliced in small pieces, and you can concentrate and take the 3D digital model, and you can actually visualize certain sections. But
Actually,
it's also
the size.
yes.
Oh,
Go ahead.
The size of the model depends on the simplification of how many triangles we have at the end of this model after optimizing it. And it's related somehow to the original environment, how it is big or small. So for small objects, we can see very light models, and in terms of, let's say, 100 of megabytes. And once we go with the environment, big environment, we can, yes, go to the giga, yes.
Very good. Thank you. Very well done. Thank you.
Yeah,
Thank you so much.
Thank you, Larry. That was a great summary, and hopefully, students, you understand. What you are doing is extremely useful for the industry, and they're looking for that skill set also. Any other guests who want to introduce themselves? Please go ahead.
Jason Marcusino from Applied Manufacturing Technologies. I'm our innovation manager here. Based out of Orion, Michigan. Been with the company 21 years now. So we do industrial robot programming, industrial PLC programming, system integration, a variety of different things for the automation industry. Kind of piggybacking off of what Larry was saying, not only is the photogrammetry good for and the engineering side, I think there's a lot of applications in sales also, being able to take the photos of the plant in the current state that it's in, and being able to place the equipment or the cell in there, and then have the customer go through in a virtual or an augmented reality manner, and be able to see that is really beneficial for them to get the feel for the size and the scale of the automation they're adding in. So nice job.
Yeah, thank you.
Thank you so much.
Thank you, Jason. Anybody else who want to introduce themselves? Guests?
Laura from Career and Life Design.
Welcome, Laura. And I see Kelly also.
Sorry, I was not muted earlier. I apologize, but good morning, everybody. Good job so far.
Welcome, Kelly. Anybody else? Okay, if you have questions, classmates or anybody else for the group one? If not, then I'll have questions too. But first of all, excellent detailed video and presentation. I was expecting that from graduate students.
Yeah,
It almost looked like a thesis presentation going on. I was saying, okay, we will have a whole day here with these two guys. But no, good one. The
I
question.
have a quick question.
Yeah, go ahead, John.
So how long did it take you guys to capture all those images?
It's around 2,000 images, took about 2 hours to 3 hours, something like this. And actually, we are looking for a cloudy day. So it's somehow you need
besides
to
the
wait.
photos, Mohammed, were taken that were not in use. Some models were built up, but after we get the output from the software, we got something very distorted.
Yeah,
So
actually, we didn't present everything we work because we don't have that much time to show everything. We actually created so many other models also.
Okay. Can you do that with a video instead of taking photos, taking a video around the model?
Yeah.
How good was that model? Did you try that?
Yeah, actually, the model with the at the end of the demo, I don't know if you saw it. It's
Mhm.
based on 5 minutes. Sorry, 5 minute video only.
Okay.
Let
So
me
that's
just go
So
to
that's
it.
a quick way to construct a 3D model, just taking a video of the 3D object and then converting it to how. So you feel like it was easy using the tools which are available, Unreal Engine and the reality capture software, that they are pretty straightforward and easy to use to do
Yeah.
all this process.
Yes.
Yeah,
Yes.
and actually here we can see this model to the left. It is videogrammetry. Actually, we captured 5 minutes video and imported it to that software and go through the steps, and that's it. And we can see
And
how.
you had good key points coming out of the video also.
Yeah.
Okay, great. Other questions, guys? I have 2 more questions, and we'll move on to next group. So one question, looking into, this is a great application for many different users. Can we incorporate AI tools in here if we have missing data in the images, so it can reconstruct the missing parts for a complete model?
Actually, I didn't see something like this, but I noticed something which is great. If there was some movable object in the scene and it appears in some images, low number of images, it will be ignored and excluded totally. Actually,
I
once
see.
I did something like this, a project, there were many cars in some parking lot, and I took images. While I'm taking the images, the cars are gone. So I continue taking images without those cars. Then once I generated the model, it was generated successfully without these cars.
Okay. The reason I asked this question was that there is the recent news from Niantic also, the Pokemon Go. If you know that AR game, that they are using the data, 3D scan data from the game to reconstruct 3D models of objects of the world itself. They're making a spatial mapping of the entire world 3D objects, and they're using AI to fill in missing data. So because you can't possibly capture every single thing of everything.
Yeah, yeah.
So this is very interesting, that if we want to look into, can we use this kind of data to fill in missing information? Because how AI can generate 3D images also from
Actually,
text and
I
all that.
saw I saw an application using a single image to generate a 3D model using
Right,
AI and these things. Yeah, yeah,
right. So there is a lot of possibility here. One last question.
yeah.
Um, are you able to get exact dimensions of the 3D object by doing this process? So if we are
Actually,
placing it in a world, we know the exact size of the object also.
for the measurement. Yeah, actually, the reality capture, it has this capability, but we need to take images with some meters in images and to replicate the distances exactly to be the same as in the reality. But I didn't test this feature actually. But yes, it has this capability.
Great, thank you. Any last questions, guys? If not, great job, Grofan.
Thank you. Thank you.
All right. We're going to move on to our next group, group number 2, and they are going to present Scanwich. Please go ahead. Share your screen.
Okay, hello everyone. I hope you can hear us and see the screen. We will be presenting Scanwich, which is an augmented reality nutrition tracker. We are group number 2. My name is Sam Walker. I'm a computer engineering 4th-year student.
My name is Sivasakthi Muthukumar. I'm double majoring in electrical and computer engineering, and it's my 4th year as well.
And I'm Holly Jane Bates, and I'm also a computer engineering senior.
Okay, so here's what you can expect from our presentation. We'll start off with a demo video, which is about 3 minutes long, and then we'll talk about what Scanwich is. We'll go over the system diagram, the food detection, how it overlays nutritional information with augmented reality, and then we'll wrap up with some challenges and we'll talk about improvements that we could make in the future.
Can you make it full screen?
Oh, hey Shiva.
Hi, Sam.
Do you know how many calories are in those fruits?
No.
Have you heard of this great new app called Scanwich?
No, what's Scanwich?
Introducing Scanwich, the nutrition tracker that identifies, scans, and displays the nutritional information for different foods.
Are you tired of doing math and trying to calculate how many calories are in your meals? Well, Scanwich's got your back.
By scanning the ingredients of your meals, you can measure calories, total fat, saturated fat, trans fat, cholesterol, sodium, total carbs, fiber, sugars, and protein. Currently, Scanwich supports common breakfast foods as shown here.
To use Scanwich, first, the Jupyter Notebook needs to import OpenCV and Ultralytics when the program is run.
Then, the webcam is used to detect the different food items.
Each food item has a box around it with the name of the food and the accuracy score.
To record each food item, the space key is pressed.
Once you have scanned all the food items, hovering over the ARC UCO marker shows the total nutritional value of the scanned ingredients.
By clicking G on the keyboard, the recorded food items are cleared out.
And that's how Scanwich works.
Here are some future improvements. 1. Video capture frame rate. Due to using individual datasets to identify each food option, the frame rate is very slow on the output. This can be avoided by training only one dataset instead. 2. Object detection issues. Usually Scanwich is good at detecting stuff until it's not. We can improve this by adding more photos in each dataset and training each dataset for longer. 3. Better UI. Currently Scanwich runs on Jupyter Notebook and the food is scanned using a webcam. This is a great prototype, but in the future it can easily be made into a more user-friendly application. And 4. Add more food options. Right now Scanwich can only identify 6 food options. In the future we'd like to add a larger variety of foods.
So like the video mentioned, Scanwich is an augmented reality or AR nutrition tracking system used to track the nutritional information about different foods. So you may wonder why Scanwich rather than other nutritional trackers and what makes it special. Unlike other trackers where you have to manually enter the foods in or search it up on a database, Scanwich takes out that hassle and lets the camera do all the heavy lifting in detecting foods. And when you're making a bigger meal with a lot of ingredients, instead of having to take out a pen and paper and doing the math on how many calories or different nutritional values your meals have, Scanwich can automatically calculate those values for you. It makes tracking your health and nutrition so much easier.
So what can Scanwich do? It can identify the 6 main breakfast foods. We got breads, eggs, apples, cereals, bananas, and potatoes. And it can tell you the macronutrients of any combination of these foods. So say you're just having an apple, Scanwich can tell you the nutrition facts for just an apple. And if your meal is eggs on toast, you can scan the ingredients for eggs on toast and it'll do the total nutrition facts for your meal. It handles all the adding and you don't need to get a calculator out. Plus, things like bananas don't come with nutrition facts labels, but Scanwich will know and it can tell you how much protein, fiber, and sugar is in the banana.
So how does it actually work? We have a system diagram here. The core of our project is on the laptop, utilizes OpenCV, which is the computer vision framework that we used in class. We have Ultralytics YOLO. We used version 8. YOLO is a object detection framework. We have a webcam connected to our laptop, and the camera is constantly scanning two things. Of course, the food, the 6 ones as PJ just mentioned, and then also we have this AR UCO marker, and this is kind of like a QR code. It acts as like a sort of identification, and so every time the camera notices the full marker, it'll then overlay all of the foods that we've inputted and the label onto the marker.
So the very first step of implementing Scanwich was implementing the food detection. And this was done using RoboFlow and YOLO V8. RoboFlow is a platform to create and deploy different computer vision models. And what we did was we found individual data sets for each of the food items that we wanted to detect. We also had the option of making our own data sets, but we found more success in finding pre-made data sets. And each of these data sets have 100 to 300 trained and annotated images for each food. And what trained and annotated means is that a bounding box is drawn around each food object, and a label is written on what that food object is. And this data set is exported as a zip file onto your computer. And from there, it's trained using YOLO V8. And YOLO V8 is a set of deep learning based object detection algorithms. And you can set the epoch size, the batch size, and the image resolution. And basically you can play around with that to get the most efficient trained model, as well as something that doesn't take too much time, because one of the issues we were running into is that sometimes training our models, especially if it had a lot of trained and annotated images in the data sets, took a very long time to create the final trained model. Once the model is made, it's outputted as a PT file, which is used in our food detection system on our Jupyter Notebook program. And here's a picture of our final output, which is basically the webcam video with the detected object on it. So once our program detects an object, it draws a bounding box around it, which is the green square that you see, and it labels the object that it's detecting using the PT files that we imported into the project. So in this case, it sees an apple. And then there's a confidence score that's right next to the name of the object that's being detected. So it's basically saying that it's 82% confident that it's an apple. And since we're using multiple data sets in our program, basically one for the apple, one for the potato, one for the banana, so on and so forth, the code runs through each model before outputting each frame, and basically overlays all the objects that's being detected on the frame. And we added confidence thresholds to each of our objects being detected. So for example, we won't display the bounding box with the label unless it's more than 70 or 80% confident, to avoid the same object being detected as two different items, or detecting something that's not supposed to be detected. And then using the items that's being detected, we calculated the nutritional data, and basically we just took like a sample nutrition facts label and labeled the most common nutrition facts, such as calories, total fat, cholesterol, sodium, total carbohydrate, protein, so on and so forth. We found the macronutrient data online and manually entered it into a different set of arrays for each of the 6 trained foods. And based on what's being scanned and recorded, we calculated the total number of calories and other nutritional facts. We recorded the different items that are being scanned by pressing the spacebar on the computer that the program's running on. And it basically created a running list of all the objects that were detected, and then the total nutrition facts were added and displayed on the final overlay. If you ever wanted to clear out all the nutritional values that were calculated, or if you want to scan a different set of items, the G key was pressed on the keyboard to clear out those values to 0.
So when you're done scanning all your foods and you want to find out the nutrition facts of your meal, you have to pan over to the AR UCO marker to see an overlay of a nutrition facts label. We use the OpenCV AR UCO libraries and functions to accomplish this. This flowchart shows the processing steps for each frame that's retrieved. So you retrieve a frame from the videos and we detect the objects. And then we see, is there an egg and do you want to record the egg? And you'll add the egg's macros to the running total for the meal. Those values are placed as text onto the nutrition facts label. And then once the AR marker is in the frame, we can detect where the corners of the marker are, and we can also know the coordinates of those corners. Then we use those coordinates to calculate a perspective transform that places the nutrition facts label on top of the AR marker. And this process is repeated for every frame in the video stream. So let's look at how the AR overlay shows up. So the picture on the right, in the real world, we just see a piece of paper with the AR marker, that black and white image. But in the virtual world, we see the nutrition facts label overlaid on top of the AR marker. And then for the picture on the left, we have the AR marker just laying flat on the table. And then the nutrition facts label is overlaid on it because we can still see the corners of the AR marker and we can still calculate that perspective transform. So because the AR marker is laying flat on the table, it also looks like the nutrition facts label is also laying flat on the table because of that perspective transform. So with any project, it wasn't completely smooth sailing. There were some hiccups. One big thing is we wanted to add another ingredient, yogurt, to have 7 ingredients. So we bought yogurt, we took pictures of it, we drew bounding boxes and labeled it, we trained a model, and then our model just really couldn't detect any yogurts very well. And that took a lot of time and energy and we had to scrap it. Another thing with adding more ingredients is it's kind of tedious adding in all those nutrition facts, that sodium, that cholesterol, those calories by hand manually. So adding more ingredients would be a lot easier if we just called upon a database. And we spent a lot of time balancing those confidence thresholds. This is pretty well described in the picture on the slide. We just have too many things being labeled as banana. I mean, kind of fairly, like Sam should be labeled as a banana in a banana costume, but maybe it could be better. Maybe it could know that bananas don't have arms and a face. And if you look even closer, the yellow wall is also in a bounding box labeled as banana. And the model should know that just because something's yellow, it doesn't mean it's necessarily a banana. So this threshold was too low. It called everything a banana. So for all our ingredients, we were playing with those thresholds to make sure not everything was detected as a banana. In the beginning, we also had some trouble with the AR overlay. In order to calculate that perspective transform, enough of the AR marker needs to be in the frame. So if too much of a corner is cropped out or you can't see a good amount of the edge, then you just can't calculate that transform and the nutrition label won't show up. So in order to prevent this, we made the AR marker even smaller, and then we expanded the nutrition facts label to display beyond the black edges of the AR marker. And that way you could zoom in onto the font of the nutrition facts label without it disappearing on you. And then sometimes the project challenges aren't even adding design features, it's about finding Python itself. And many times we dealt with NumPy array shape errors and broadcasting errors.
Here's a list of future improvements we would make. A lot of these were already mentioned, so I will not spend too much time on them, but you can sort of imagine, ideally this would be a phone app. You know, you'd go to the App Store and download this. And if you imagine the frame rate that we had, you know, it was like 1 or 2 frames a second at its worst. That would be a very poor user experience. So we would want to increase the frame rate. We've already talked about how to do that. We would balance out the thresholds a little bit better. We would ensure better training accuracies. We would also remove the need for the AR marker. That was that little QR code looking thing. Ideally, you don't want the user to have to like print out something like that. That was just for us. That was like a quality of life thing. That just made it easier to interface with augmented reality. But ideally, you hold a food, and then next to the food, it shows the label on your phone. Also, again, adding more foods, you know, the ideally is some sort of database that has hundreds and hundreds of foods. And then also, we understand it's named Scanwich, but it doesn't even really have the capability to scan a sandwich. So hopefully one day we'll add that.
Quick summary on what we just went over. There's three main components to implementing this project, which was first the object detection, basically training a model and using that model in our design to detect the object that's being put in front of the webcam. Then retrieving and calculating the nutritional information for the overall meal that we're trying to scan, and then overlaying that on the AI marker, which PJ went over. And in summary, Scanwich is a great prototype of a nutrition tracking application using machine vision and deep learning, and it has the potential to become a mobile application or something a bit more user-friendly if provided more time. And with that, we would like to thank you guys for listening to our presentation, and feel free to ask any questions about our project.
Thank you, group number 2. Good job. That was a fun video and project. You want to unshare your screen? So one comment that if you implement this on a smartphone, it's going to complain every time you eat fast food then. Bad nutrition values. All right, we're going to open up for questions from anyone. Please go ahead if you have questions for the group.
All right, so I started with the first, but I'm going to continue. Very, very well done. I was very impressed, and the framework that you created specific for the Scanwich, it's very, very important. I will give you two other examples that I was thinking as I was looking through your presentations. Exactly the steps that you follow, probably a little bit much simpler, can be if you have a book, you take a picture of the book, and automatically that book will provide you all the information about when was published, what's the price, or if you want to take the book to put it into like an Amazon to sell it out. So will it be an app on the phone that you take a picture of the book, automatically will be published for you with the right price, with the right. It's very impressive, the steps and the complexity actually you have. It's much more deeper. Another example will be, which I know that it's going on right now, it's about car industry again, because that's what I'm living into. So lots of used cars, after we returning back to the dealers, there is a systems where they created just by taking a picture of the car and the VIN number, automatically that car become it's introduced into a database, and that database automatically provide the history of the car with, like you have the recipes with all the calories and everything, and provide the pricing, and they provide suggestions for the next customer to be sold out. So what you created right now has a lots of potentials for many other segments. So around us. So very, very well job done. From here, you only can take it to the next level. So thank you very much. Very good, very good.
Thank you, Larry. That was great summary and comments. Any other questions for the group? Okay, I have a question, group. So when you're calculating the nutrition value, do you take into account the size of the object to scale the nutrition, values? How would you, if you don't, then how would you go about doing that?
So we did not. We found YOLO to not be accurate enough. It would depend on the framework we're using, and you guys can correct me if you have anything to add. But it gets tricky when you consider the amount. And so, is it by weight? Is it volume? With liquids, it's challenging. And so this shouldn't be used too heavily. It should just more so give you an idea of exactly kind of, okay, this is one serving of this food. There's a side of it where you can implement, I'm gonna press up 2, 3, 4 servings. and that would be on the user side rather than the recognition. But I mean, when we thought about like a sandwich itself, there are things inside of a sandwich that you don't even see. And so how is it supposed to recognize that? It's actually impossible. When you think about mixing certain things together, it becomes impossible. So we took the approach of scanning it before you combine them. But even then, it's difficult, and you can't really tell based off of the size of the apple. The best you can get is identify maybe the type, and maybe the size too. We could do size recognition, but as it stands with YOLO, that's very difficult. We would probably need to pivot to a new framework.
Right. So that, yeah, you're right about that. You know, as humans, when we look at the food, we can kind of estimate the serving size to scale our nutrition value. You could teach AI to do the same. So yeah, that will need more training and estimation of size and serving what it's seeing. So yeah, so there are potential. Absolutely, if you make it a real app, then you can incorporate those features also. Any other questions?
Just a suggestion, Samuel. So, like you said, to be able to actually understand the weight and the volume of a certain food is going to be very hard. It will be very complex recognitions for you to be able. But if you are combining that with other factors like the time when you serve the meal, with the environment, you know, what type of other foods you have around, what's the size of the plate. So you'll be able to generate a training model that will estimate that for you. We're not going to be 100% accurate, but will be fairly close. And I'll make a parallel between your application and what I'm living here in the robotics industry. We were trying to understand the performance of the robots to be able to predict if they will have a potential failure or not. And definitely that comes with a training. Like you have here a training model, will have to create certain motion range on the robots. And based on the readings of the motion range, we'll be able to determine a health pattern. But that required a separate time outside of production and required to be with parts or without parts. So it was fairly complex. So in the middle of the night, you'll see a whole body shop with robots moving. Was okay, but was not necessarily a practical solution. So we were trying to really understand the robot behaviors based on actual production motion of the robots. So it was not accurate, didn't provide the same data, but was sufficient for us to use that type of environment to really develop a pattern about robot performance in a daily basis and generate a message, a warning message in case it was something abnormal. So it'll be the same thing for you. You may have to train the module, not necessarily based on actual foods, based on what happened around that particular meal, and they'll provide more data to estimate.
Excellent point, Larry. So you could, I was thinking that you could train it for a person, what foods they tend to eat, so they can keep track of their normal day. So yeah, it's a lot of potential there. But you know, I was just worrying about, you know, what is the nutritional value of that huge Sam banana we saw at the end. That would be like throw everything off the charts.
Very good. Yeah.
Okay, great presentation, guys. Good job. Okay, we're going to move on to group number 4 because at the end we'll have group 3 and 5 combined. So group number 4 is going to present host helper. Take it away.
Okay, can you see my screen? Oh, okay, wait. Okay, so good morning, everyone. We are group number 4. My name is Francesca Cipriano.
I'm John Azam.
And our project is Host Helper, the seamless seating detection. So our program is implemented on a model restaurant where it is divided into zones, and each zone has features that we track.
This specific restaurant is divided up into 4 separate zones with 1 table in each zone. Each zone has its own timer count and people count that counts the number of people in each zone. And if there is a person detected in the zone, then that timer starts. If there is no people in the zone, then the timer is going to be at 0. We do have a master count all the way on the left, which actually counts up all the people in the restaurant to know if you are at capacity or not.
Okay, so to start off, the program that we chose for our machine vision project is a useful program that could be used to make the lives of restaurant employees easier. So the three main features that we chose to implement is to track the customer's duration of stay in each of the zones, the number of customers in each of the zones, and the total occupancy of the restaurant in order to be used for like safety purposes or if there's a maximum capacity or just that type of stuff. So the IDE that we chose was PyCharm. And we use the YOLO V8 library with an already pre-trained data set. So we created a software flowchart in order to simplify how the code was going to be written out. And this exact flowchart is used for each of the different zones. And how it works is it first keeps looking for if there's a person in each zone. If there's not, it's going to keep running in a loop until it finds one. Once it does find one detected, then this is when it starts the zone timer. It updates the zone count and it updates the master count. So these counts keep getting updated every loop.
So building a restaurant was not within the scope of the class, so instead we opted to build a model restaurant. So we just took like a piece of wood and all of our little model people that we have, which were just pre-bought from Amazon, they have little pins in them. And so we just drilled holes into the wood and we were able to put the people into the wood, which you saw me fumbling around with in the video. So the wood, we preemptively stained it a darker color because something that we were concerned about was like the wood was a very similar color to the people, and so we were worried about YOLO not being able to detect features of the people like with the wood in the background, so we preemptively stained it. Now as for some of the challenges that we had, which that ended up being fine, but so we originally wanted to be able to count plates in addition to people and being able to look at if a table was like clean or had plates on it, but it was extremely difficult to actually do that because the quarter was like we wanted to use quarters as plates. They were way too small for the camera to actually be able to see. And then as you can see on the right here, another issue we had was when the people were lined up vertically in the perspective of the camera, it would sometimes see them as just one person. And so that was another thing that we had. And our people also look kind of like carrots, which YOLO thought they also look like carrots as well. So every so often it would see it as a carrot. Or as you guys saw in the video, the people who were kind of on the outsides of the wood, it would sometimes not recognize them at all. And that kind of is sort of tied in with my next point, which is that it was extremely difficult to get like the camera to be at the perfect angle to not only see every single person, but to also detect every single person. There were brief moments during the video where every single person was being seen at the same time, but it was pretty difficult to set that up. And so in like a real restaurant, that would be something where you might have to consider multiple cameras or it would be definitely a consideration. And of course, for us, we ended up using PyCharm because for Jupyter Notebook, we were just having difficulties getting all of the libraries to work in it. So we ended up using PyCharm and it was much more simple. Now, as for ways to advance the software or ways to improve it, adding a time lapse for So like if you have a server check on a table, a timer would start and basically just see like when the last time they were at the table was. And then also a heat map of seeing like what the busy areas of a restaurant are, or like the busiest tables. That would also be super useful information for a restaurant to know. And then having like empty table detection, so actually being able to, because right now we do have a count of all of the people in an area, but we originally wanted to also be able to say, like, if there's 0 people at a table, then have some type of status indicator for the employees of the restaurant. And then, of course, most importantly, is having a more robust system to be able to properly detect plates.
Yeah, so in conclusion, we do feel like this program would have the potential to be used in the real world, especially with the people counting. Now, something that we noticed when we were first trying out the YOLO, the pre-trained data set, was it worked better on real life objects and real humans. It kind of never faulted in detecting a person, but when it came to the actual like little figurines, it did have some difficulties. So trying this out in a real environment could possibly have more success with it. Now, we did have some limitations, but there is ways for this program to be advanced and developed and even be more specific per what a restaurant wants and what specifications. Now, we were also coming up with some other ideas of where this program could be used. For example, we thought of some things like a sports arena, how it's divided into zones and you could count the people that way. Or even something like an amusement park where you use a heat map to see where the busiest attractions are and the most popular ones. Thank you. Does anyone have any questions?
Thank you, Group 4. Good job. All right, we're gonna open up for questions. It was a very interesting demonstration and application. You guys came up with a creative thing here. All right, let's go ahead if anybody has a question here. Go ahead, Steve, introduce yourself and ask the question.
Hi, I'm Steve Kinney, Director of Training Compliance and Technical Solutions for Smart Vision Lights. Very interesting. I applaud the groups. I think all these presentations are very creative. I think the one here, obviously, the detection of the people and the plates is the key. And since, of course, we're on the machine vision side of things, I wanted to make a few points or ask the group some. So I think there's 2 things. One is the group pointed out there's detection of real people in real space, which is a little bit different than the detection of the people in their model world. This is the people in the model world's more a machine vision type of problem where we're kind of like inspection or something compared to real people in the real world. So there would be differences there. But in the case of the model in this example, I wanted to ask them if you had to improve your detection in the model space, what they thought they might do to do that.
Yeah. So originally, like all of our people were showing up in red, but actually some of those people were not necessarily people. They could have been carrots or birds that we mapped them to be people and to count as people. So especially with the quarter at the beginning, it could have been partially our fault because we decided that we wanted to try a quarter instead of something that actually looked as if it was like a bowl or a plate. But not only did it see it as one thing, but it kept seeing it as like 6 or 7 different objects that we were going to have to map into one. So that's why we kind of decided to get rid of the quarter, but it would definitely have to be improved in the software to detect like non-real like people and detect other things.
Well, I was gonna add as well that we used like the pre-trained models as well. So we could have also used like trained our own data set, which we tried to do, but we couldn't get it to work. It was hard.
We attempted to train our own, but then we thought that it might just be easier to use a pre-trained one and just map the different objects to each other.
That's an interesting point. So the pre-trained ones, the models are probably not quite what were pre-trained as well.
Yeah.
The thing I was trying to see if I could elicit from you was if you were dealing with those models and the plates and the table or the wood was different than the floor, obviously, and that's why I made the distinction, this is more a machine vision where you're in a fixed model environment. The other answer to that, and I see this a lot, is lighting. So I hear a lot from the AI models, well, we trained it for lighting, or we trained it these variations,
Yeah.
but even with all that, it was hard for you guys to train those models, right? So then the thing I would like to invoke is think about in those cases, what if I'd used red light, for example? The stain of the wood would match and become maybe a little darker, and the model that was plastic and reflected light in a very wide spectrum might actually become brighter against the background wood. So there's ways to light the type of lighting and placement and stuff as well.
Yeah. Which we did kind of experience that. We didn't try any colored lights, but when we were originally trying it in our engineering center, we were by a lot of windows and during the middle of the day, so it brought in a lot of light. And those mini figurines are very reflective, so a lot of them weren't being seen. So that's why we ended up, our final video was in like kind of a darker room, so there wasn't as many shadows and reflections.
That's also a very good point, because I've seen cases, Tesla and other places in their factory, where daylight from the window disrupts. When you're deploying machine vision systems, controlling the lighting to get the right result in detection is key, and ambient lighting is actually pollution. I also hear that, oh, the lighting is very good in here, we just use the ambient lighting. But in like automotive plants, the mission critical stuff down the floor is on a different power system than the overhead lighting. So how would you like the overhead lighting, which is on mission critical, to go take a production line down because machine vision stopped working in that case, even though you were running off of critical power? So that's a very valid point. Just to round that out, in daylight situations, we often use either long pass filters or use like a red light and narrow band around the red, where you're blocking 90% of the energy and you only have to overcome a very narrow band, and you're putting 100% light in that area to solve problems.
Excellent point, Steve. And you're right. I mean, we talked about in the class about a structured environment and a non-structured environment. So in a structured environment, in a factory setting, we need to take into account all those things are very important. Lighting, your camera, lens, where did you place the camera, how clear is your image, and all that stuff is extremely important to get information out. But then once you have that done, your results are almost 100%. That's what you're expecting in that environment, that you don't fail, your vision doesn't fail. So excellent points there. But in a non-structured environment, the artificial intelligence, machine learning models perform better, because now the lighting is not under our control. The models look very different and all that. So, the better trained machine learning models do a marvelous job. So I think in your case, group number 4, that the YOLO model, which you use for people recognition, was trained on real people. So it will do a great job of recognizing people in all kind of lighting. But those models did not look like people. They didn't even have, facial, they just had the shape, and that's it. The contrast, the face, the clothes, they were not there. They were not even painted. So it may have a hard time recognizing them as people, but it still did. So which is great that it did that. So that tells you a little bit about the training model, that maybe it did look at some people who were like statues, standing like statues, and then it kind of recognized, oh, this is a person. Anyway, so yeah, machine learning always is, the key is where is your data coming from and how well trained is your system for reliability. So it is interesting that you did make it work for those small little people, and that you could do your project. And I know you only had 4 weeks to do all that, and not enough time to train your own models and all that. So good job there. Other questions for the group? All right, so one last question before we move on is how would you improve the accuracy of counting? Let's say you have a good model. Sometimes a person walks away to the bathroom or there are other people standing in between tables. How would you improve all that? Like you're trying to count people on the table and keep a running count. Like, okay, we have 6 people seated on the table. So any ideas to improve the accuracy of your application here?
As for the people that are in between, that one you could almost you'd have to have something where it kind of looks to see, like, if they're bouncing in between areas, some type of indicator to see, okay, well, they've spent more time in this area, so we'll count them for this zone. That would be just
Yeah, we talked about this in the class also. Remember when we talked about ROIs, regions of interest. So if your camera is fixed, you will define zones on the tables, and this is inside that zone you're counting. Outside of that zone, you're not counting. So it can help you improve, only counting people who are at the table, not walking around anywhere. Any
Yeah.
other way you can improve your accuracy?
I was gonna say, I know right now how ours works is that it takes the box of where the person is, and wherever the center is located, that's which zone it's located in. So I guess instead you could change it so it's not necessarily where the center is, but where most of the body is, to know which table it's at mostly.
Right.
Also,
Exactly.
maybe you could have something different where, so right now we just chose to put one table in each zone, but how it would be is you could have like multiple tables in each zone, but have a different box around each table specifically. So then you could detect which people are included in a zone versus which people are included at a specific table.
Right. So these are some of the ways you could make your application more robust and more accurate. You could even keep track of historical data that, okay, 5 people were seated. If for a little while it's 4, maybe that person went to the bathroom. So, and then, okay, we got 5 back. So you don't instantly like something is fishy. No.
Yeah.
Look at the historical data and keep a running count and see, okay, things are still okay. This is what we have. So good job, guys. It's a lot of things to think about that, using this technology, you can leverage it to do a whole lot of interesting applications. So good job, guys.
Thank you.
Thank you.
All right. So we have our last group, combined groups 3 and 5, who are going to present next. And they will be presenting secure access safe via biometric law. Go ahead, take it away.
Can you guys see my screen?
Yep.
Okay, so slideshow. So our project is secure safe access via biometric scanner, biometric lock. My name is Brendan Fennon.
I'm David Kosa.
I'm Rishi Tripathi.
And Josh is in here as well, Josh Pagonis. So our project, we have a demo video.
Functionality.
So let's begin with the current lock screen that we have displayed. We have a scan button and an exit button. No processing is performed on the lock screen until you hit scan. When you hit scan, it performs face detection. It determines if there is a face present or not. Alright, let's try scanning when there's no faces present in front of the camera.
Wow, it's not a face.
Let's say somebody prints an image of one of our existing users in the database. Well, we obviously don't want them to have access to this safe, because then that would defeat the purpose of having the depth camera and making a secure safe to begin with. So, let's see what happens when we hit scan. Wonderful. Nothing happened. So essentially what happens is we have a depth map that gets calculated from the monochrome camera data. Essentially what happens is once the face is detected, and we can see a face clearly on this image that's printed. Once the face is detected, it calculates the average standard deviation for the depth found on that face. So we take a region of interest, specifically for the face that's detected, and perform the calculation. Obviously, for a flat image, that value will be quite low, whereas for a real face of a person who is there in person, it will be much greater. Using this information, we can determine if a face detected is fake, which is 2D, or real, 3D. All right, let's do this on the Raspberry Pi now. Josh has hit scan, is identifying him, and he's logged in. So we can unlock it, as shown, and then if you open it, boom, it's open. We can lock it again, locked. All right, let's take a look at the inside of the safe. As we can see, it is still locked after hitting lock. All right, let's take a look at the inside of the safe. Go. Oh. It's same thing.
Another one.
So let's test it out. Let's see what happens if we hit scan when there's no faces in front of the camera.
Huh. It looks like there's a face there.
Another one.
Hold on. Where is this? Okay. So this is future of secure storage technology. So it's very important to have security for personal items. You know, most people want to secure their items in some way, whatever it could be jewelry or money, whatever it could be, social security card and vital information like that. There's already a lot of technology present that bypasses pre-existing security measures, and people are able to break into these systems even more often every day. It's evolving every day. And this technology, it's easy adaptable to new security technologies.
Okay, now we'll talk about the overall physical design of the safe. So we wanted the project to be self-containing in that the safe itself would include all the components being a depth camera, a servo lock, and a Raspberry Pi. This included embedding the Pi with an 11-inch display touchscreen inside of the safe. The design of the safe started with a simple paper sketch, which included rough dimensioning of the safe with the Pi's touchscreen in mind. After dimensioning, we designed the safe in Fusion 360 and added clearance to the parts so that each component would fit properly when assembling. Using a 3D printer, the safe was printed piece by piece. Some pieces needed heat set threaded inserts, and screws were required to fully assemble the safe. Also embedded in the safe wall is a servo motor that acts as the lock for the safe. To lock, the servo's horn slides into a slot that's notched out in the safe store. In the next slide, we'll talk about the user interface.
So the GUI, graphical user interface, it was designed for easy facial recognition. So it needs to be simple, but gets the job done. There's minimum touchscreen friendly interface, and it was built with Python's tkinter module. And here you can see there's two screens. There's a lock screen, which shows the camera view, and then there's two buttons, scan and exit. If you are granted access into the system, there's a label identifying who is logged in, and then there's a lock and unlock button for the servo motor for the door, and you can exit out back to the lock screen where someone would need to be scanned back into the system.
So initially we selected the Pi camera instead of the depth camera that we have now. However, one issue with it is that it can't create a depth map that we need without having a second one. So our current camera, the Oak D camera that you can see on the screen, is a depth camera where the D stands for depth. So it can produce RGB frames and it can also produce depth frames indirectly. Some of the benefits of having this camera is that it has a library called Depth AI, and it also supports OpenCV functions that we've been using. So it has a variety of camera operations like RGB and stereo camera data control, and also just being able to control the camera in general. So for example, frames per second. It also has depth sensing, AI and neural network support, vision and image processing, and data streaming and processing, and much, much more. On the left and right of the camera, you can see that there's two sensors there. Those are the monochrome cameras, and they capture grayscale images of the same scene, but just at different angles. And the process for getting the depth map is they rectify the images, so they're transformed so the corresponding points are aligned horizontally, and then the pixels in each image are compared to calculate disparity. And disparity is just the difference in the position of a pixel between the left and right images captured by the monochrome cameras. Lastly, for this, the depth calculation uses the camera focal length, the baseline distance between the cameras, and then the disparity value that we just mentioned in pixels. So why do we need a depth map? Well, we need a way to determine if a face is 2D or 3D. And the first step in the process is determining if there's a face present before we even do any further computation. So we need to use a pre-trained neural network called MTCNN, which has a built-in face detection function. This outputs a region of interest consisting solely of the face detected, and assuming that there is a face present, it will calculate the standard deviation of the depth in this detected ROI to determine if the face is 2D or 3D. One major factor in this is light. So dim lighting reduces contrast and makes objects appear darker. And as a result, there's fewer discernible features for stereo matching. And this results in poor disparity calculations, less accurate depth maps, and increased errors or gaps in depth estimation. In especially dark conditions, depth maps can become blurry, noisy, or incorrectly represent object distances. So going further into this, dim lighting settings can reduce the contrast, as I mentioned, on our faces, and that reduces the fine details and causes poor matching of points that we mentioned before in the process between the two stereo cameras. And with less reliability in finding those corresponding points, disparity values calculated might be less accurate, and that makes the depth map less accurate too. On the other side of this, there's also harsh and bright lighting that also causes loss of detail, and that can cause glare or reflections, and that also hinders the matching process. As we can see on the next slide, we can talk about how information is handled. So this is very different from what we're used to, or at least slightly different from what we're used to in Jupyter Notebook. We have to create what we call a pipeline, and that defines how we manage and define data flowing in our main Python script, and that's data flowing between nodes. What are these nodes? Well, they're basically reference points that we're creating to define certain processes or operations. And as you can see on the screen, there's something called an input node. An input node is basically connecting the physical camera to the pipeline that we're creating. So we're creating that connection from the physical world to the programming world. And it acts as an entry point for the data from the camera. Just as a side note, these never store data, and that's going to be important for the next thing I'm talking about, which is the output queue node. Essentially, they're buffers or containers which store the results or information from the input nodes or from previous nodes that do processing, and they can be accessed at any time. So this is important because we have a stereo depth node that you can see down in the bottom right. This is a processing node which calculates the depth information for each pixel in the frame that's captured. It calculates the disparity and then uses triangulation to estimate the depth or distance between the camera and the object in the pixel. So in the next slide, we can see that there is a face there. So the main method of determining 2D versus 3D is the standard deviation, like I mentioned before, of the depth values for every single pixel in the frame. Essentially, the depth map is a matrix of depth values assigned to each pixel in the frame that we have captured. And we can perform the standard deviation calculation on these depth values, and we'll generally get higher values for objects with higher variations of depth. So for a real face, there's a lot of differences in depth between my nose and my cheek, whereas for a 2D image, it's all going to be flat. So there's not going to be much of a difference. There might be slight variations just because of error, but generally it'll be lower. So we have this original frame. You see the face outline captured on the screen. One issue is that we can't guarantee that the background will also be flat behind us, and it won't have an impact on that standard deviation. How are we going to ensure that that calculation is going to be only focusing on the face and not all the stuff that's happening in the background? Well, on the next slide, we can see that there's an outline, a region of interest, focusing solely on the face. So the face is detected using a pre-trained convolutional neural network, as I mentioned before, called MTCNN. MTCNN stands for Multitask Cascaded Convolutional Networks. And that's been trained for hundreds of thousands of faces and already in like 32,000 images with around 98.3% precision. We didn't train this, it was pre-trained. And so what happens is the frame is captured, it's inputted into that CNN, and it outputs data for the bounding box, as you can see on the screen, for the box width and height, along with the top left coordinates of the bounding box. So the original script, if there is a face present, then it'll return all that information. But if there is no face present, then it'll return an empty list. Our original script that performed this operation was written in Jupyter Notebook, and it aimed to basically calculate the standard deviation continuously. So if a face is present, it'll perform the calculation and determine if it is 2D or 3D. And if there is no face, then it won't be able to calculate the standard deviation, obviously. So what happens is, if you press the P key, it'll toggle to pause the frame, and it'll also stop the standard deviation calculation, determine if the frame is 3D or not. But then there's also pressing the Q key, which quits the entire program. So when the program is paused, RGB and depth frames are kept constant in the window, so that way you can see what value you had last, and also the standard deviation as well. So we will be taking, assuming that there is a face present and it is 3D, we're going to take the frame that we captured last and put that into our facial recognition CNN on the next slide.
Hi, I'm Josh Pagonis. I was previously booted out of the meeting, so I didn't really properly introduce myself, but I'll be talking about the convolutional neural networks. So we essentially created one, or at least mostly a model from scratch, other than like the MTCNN portion. And when we were doing so, we included over 7,000 images of us, each split into training, validation, and testing. And the way we went about training our model is we included 70% of those photos as training, 15% of those photos as validation, and 15% as testing. As we were training, we made sure to set it to 50 training epochs. And overall, after enough time, eventually the model started to become very, very accurate with like a 100% training accuracy, a 92 validation accuracy, and most importantly, an 87% testing accuracy based off of all the photos we took. Now, obviously, with having a convolutional neural network with over 7,000 photos, naturally, we'd run into a multitude of issues. First of which would be including very long training time, especially if you're doing it in something like Visual Studio Code like I was. Typically, Jupyter Notebook or Google Colab is much faster, but I already had like an IDE set up for the project in VS Code, so we just went along with that. A lot of maintenance was also present since it took multiple training iterations just to get a high enough accuracy. This is mainly had to do with the fact that we didn't have enough like dropout layers, or like a learning rate wasn't present at all. And I'd say more importantly is that we had to convert our model into a .blob file because the OAK-D depth cameras architecture specifically has to run a model in more so of a like TensorFlow light type of architecture, but even then it would still have to be converted to where it could read like a .xml file and a .bin file individually, and then properly have the neural network implemented that way. Now, solutions to work around this mainly just was involving adding dropout layers to reduce training overfitting, and then implementing a learning rate schedule to minimize any and all training and validation loss. At first, it was like getting a losses between like 11 and 14, but then after like multiple training iterations, we see at the very, very end that it's getting a loss of like less than 1 in both aspects. Now, the only other thing that would be worth talking about for this project, at least for the implementation on my end, would include like implementing the servo motor control logic. So we hooked this up to our Raspberry Pi to act as our lock. And our main issue with trying to get that situated was trying to find the correct PWM ratios for locking and unlocking. All in all, this was mainly just about doing proper guessing and checking. Previously, the PWM ratios were around like 12 and 6.5, but after enough, like I said, guessing and checking, we were able to get it to a nice 10.5 to 7.5 to properly have it to unlock and lock. Yeah.
Okay, so the integration involved combined detection, facial recognition, and servo motor actuation code, as we did a divide and conquer approach for piecing together the main program. Essentially, we each tackled the smaller sections of the main program before creating the final version. Some of the smaller Python scripts required specific dependencies based on their functionality. For example, for the facial recognition, TensorFlow was required to send a frame through the convolutional neural network. So creating a virtual environment that included all the dependencies fixed any compatibility issues when piecing together the program. We ended up successfully implementing the high-level flowchart shown here. So next we'll talk about integration issues and solutions. So the main issues of the project revolved around integration. For portability, our initial program was written on a 64-bit machine running Windows, which was able to handle the full-size neural network. To integrate it onto the Raspberry Pi, though, we had to downsize the neural network using TensorFlow Lite. This led to an optimization, which involved quantizing weights of the neural network from 32 bits to 8 bits. When integrating, we also came across a lagging live video feed. We determined this was happening due to the 2D versus 3D calculations being applied to every single frame. To fix this, the program now just performs the calculations once the scan button is clicked on a single frame. And lastly, we had the GUI lock up, trying to display the frames of the depth camera, while at the same time running the tkinter GUI within the same thread. This was fixed by threading the video feed separately from the GUI.
In conclusion, machine vision can be used for a variety of applications and is highly capable of advancing current technological systems. Creating and testing full functional convolutional neural networks requires lots of images and modification and lots of pre-planning required. And machine vision is super cool. Thank you for listening to our presentation.
Thank you, groups 3 and 5. Great job. Want to unshare your screen? So yeah, a great project. It's a good combination of machine vision and ECE, since you guys also use servo motors and all. So good job there. Fully functional biometric safe, eh? Okay. We are open for questions. Anybody wants to ask questions for these two groups? Please go ahead. I hope somebody asks, because it will save me asking them questions. Right, very quiet group here. All right, I have a question here. Okay, so you guys use depth camera, 3D depth camera, to distinguish between a 2D, a photograph of a person's face, then a real face, right? Now, if you have a statue of a person, 3D statue of a person, would it get confused?
Yeah, it probably would get confused because you would run through the 2D versus 3D detection, and it'd run the standard deviation, and it would detect the statue as 3D. So the only other barrier that could possibly stop that from happening is if it were to detect a face, because if the face is not detected, it won't run either. So if both of those boxes are checked, then someone could get access into the system if they were to have a 3D statue of one of us four.
Okay, so how would you go around that to make it even safer? So would you trust your valuables in that safe if somebody does that?
In that case, no. So what we could do to improve that is to make the neural network more robust to differentiate between a statue and a real person, which would involve more training, more data inputs into the neural network.
So if I ask you, what would be a distinguishing feature between a live face and a statue face? That is something obvious.
Would be movement. No person is totally perfectly still. Their eyes move, they blink.
There you go. So eyes blinking, and there are neural networks which actually track facial features, your eyes and all. So if you run that and see no movement, then obviously it's not a real face. It's a statue of a face. So you could add layers of more security to distinguish between a 3D printed face and a real face. And obviously, I mean, there could be other other layers you could add for a much more secure. But I hope you guys going through this project understood that it's not just a simple, taking an image of a face and yeah, I recognize the face. For secure types of applications, you need to add layers and layers of security so that you cannot fool the system. So good job there.
If I could add one more thing.
Yeah,
could
go
also
ahead.
use a thermal sensor, because
There you go.
if we have a heat map, that statue is not going to emit any, it's going to emit pretty much constant heat, whereas for us, it's going to vary quite a bit. So we could use that information as well to determine more easily if it's a real person or a statue.
Right. So again, a very sophisticated statue could have heat, thermal. So yeah, I mean, how much are you willing to invest in a 3D printed face which looks like the real person? That's
Right.
like those spy movies where you take the retinal scan and you can add so many things to it. But yeah, you're right. You're on the track there. I had a question about that CNN which you use for face detection. It was done on 2D faces, right? It wasn't done on 3D faces.
Sorry, could you repeat that?
The convolutional neural network model which you use for face detection was trained on 2D images, not 3D images, correct?
I believe that's correct. Yeah, I believe that's
Yeah.
correct.
Yeah. So maybe I don't know if you could make a CNN model which actually takes the 3D data, which is coming from your 3D sensor, and train a neural network which is not only just looking at the image but also the 3D data to make a very robust 3D face detection. So there are possibilities here. What level you want to go, what security level to make it foolproof against somebody trying to trick the system, because we are talking about very secure systems now.
Right.
So I hope that gives you some food for thought. Like when you are doing these type of applications, you gotta explore many avenues and all. So good job in doing all that. More questions for the group?
I would actually like to add is that we were thinking of maybe doing like videos as a means for training our CNN, but the problem with that is there's just way too much like data, or at least like it'd be too much storage for how our scope for our project would be. And since if we were to use like a video, we'd be able to like move the camera in like more so of a three-dimensional space as opposed to just like taking snapshots.
No, I agree. I mean, you guys had a limited time, so I didn't expect you to build a very sophisticated trained model here. But you guys, at least you're thinking about it. What would it take to get to the next level here? Yeah. Steve, you had a question.
Yeah, again, very impressive, especially given the time frame here. I had two things to point out. I was curious if they took parallax into account. I think you kind of touched on it between training on the 2D model and the 3D wrap, but they were taking the face, they were using the depth map and stuff. Did they ever consider, parallax or what they thought they'd do if the person really is moving and they turn their face a little? You're getting different depth information, and same thing, the points from my nose to here are being affected by the angle to the camera. How did you guys handle parallax at all, or how would you handle parallax? And then I have another comment about the skin thing here after that.
I think our system is mostly focused on front-facing faces, obviously, for at least our project. But yeah, that could be a problem because once you look at the side, it's a little more flat compared to straight on. So that could be a problem for our system. That is something we would have to implement changes for or adjust. So we could have like a way to recognize if there's more of an angle and adjust our threshold based off of that. Because if it is at least somewhat, if we can get that angle, then we can be able to account for that at least.
I would like to add, initially when we were training the neural network, we did try and add a ton of different photos with different angles of our face, looking up, down, left, right, and then with some perspective shots, but we were having accuracy issues and we needed more photos, so we opted to just do a ton of just front-facing shots instead for accuracy.
And I think between the two, you stumbled on that a little. There'd be, I'd say in an engineering sense, know your limits of where your accuracy was in there find them, and then maybe just as Rishi suggested there, maybe put a detection in. So maybe you don't have to correct everything, but if I know I need to be front facing and I know I have, it's a cosine function, so I have some tolerance before it starts getting crazy. Maybe if I know it's good within here, then between triangulating off the nose and eyes or something, I can decide what my angle is and just limit it. If I'm turned too much, you just reject the image till they face the camera again or something. So I think those are great answers. The thing I wanted to point out about detection, and the thing I'm thinking, you know, Hollywood stuff here and Ocean's 11 kind of stuff. What if someone comes up to your safe here with, you know, Hollywood level latex mask on, where they've got all the dimensions and all this, and I'm hearing thermal sensors and other things. I just want to point out again to get you guys thinking. And again, my expertise actually is mostly in cameras and only about a third of my career in lighting, machine vision now, but always be thinking about the lighting and what happens out there. I actually worked on a project for one of the big defense contractors where they made a camera to detect human skin. And you can do this by being out in the shortwave infrared. They didn't want to use long wave and higher end systems, so they use shortwave infrared, where there's both water detection and some skin properties. And basically, they found two narrow bands, one out around 1200 and one in the 1450 range, where, you know, if you were a plant, you might reflect in one of those, but not both of them. And other things, the rocks and organic stuff tend to absorb in both of those. So what they basically did was do fast image. They built a filter that had notches only around those 2 points, and went out there and did fast imaging and basically did some Boolean math around those 2 filter points. So if it was either or neither, then it wasn't what they wanted to highlight. If it was both, they at least highlighted that in the video and said that could be skin and a person over there. So, you know, there are techniques out there for this kind of stuff. And I just wanted to throw, I'm listening to all the ideas. I would just want to throw that out there. There's actually practical skin detection.
That's a really good point, Steve. And I think you should also come to our next presentation. One of our groups is going to present like monitoring heart rate by looking at the face. So you could actually see blood circulation and use that for, see, is it a real face or is it a mask when you won't see that? So you're right, you know, there could be layers and layers of security levels which you can add. But fantastic job, guys. I believe you guys learned a whole lot doing a project like that. Everyone, you guys did fantastic job. Any last comments from our any other guests?
I suppose something I'd like to add is that in more so of the context, whether that be with like detecting a statue or detecting like somebody that is unauthorized to get into the safe, something that I also really wanted to implement would be like a cosine similarity function that would essentially determine, okay, is this going to be a little more over 0.5? And if it is, it would most likely point to one of the 4 registered users within our CNN, being me, Brendan David Arishi. But well, unfortunately, time constraints, as I said.
Agreed, Joshua. And like I said, you can add layers and layers of security. We're okay with the project you did. All right, Laura, you had any comments? Last comments there?
Well, just really impressive work. Really, really cool to see. It sounds like you guys are training animals, which sounds a little kind of creepy. The way you keep talking about training, and it's kind of boggles my mind. But I have a lot of you that have emailed me your group information so that we're going to put it up on the LinkedIn group. If you haven't done that yet, send it my way because we'll get those up in the LinkedIn group. So thank you. Great job, everyone.
And thank you. We are over time, our time limit. I hope everyone enjoyed your co-workers, co-classmates presentation. So make sure to come next presentation. We have 5 more presentations, and I'm really, really excited to watch those also. So have a great day, everyone, and we'll see you on Thursday.